welcome to this explainer. Look, every single day, billions of us tap, swipe, and scroll on our smartphones without really giving it a second thought, right? It feels totally natural. Honestly, it feels a little bit like magic how this flat piece of glass just instantly knows exactly what we want to do. But beneath that glass, it's not magic. It is an absolutely extraordinary system of electrical engineering and physics. So today, we're going to explore the invisible electrical spark happening right beneath your fingertips every single time you pick up a touchscreen device. Let's dive in.
So let's just start right off the bat with a really fundamental question. When you press an app icon, is your phone actually feeling your touch? Well, I kind of want to break this illusion for you right now. Because despite the fact that you are physically tapping and swiping against that glass, your phone isn't feeling physical pressure at all. No way. It's not detecting a mechanical push like an old-school keyboard. Instead, it's actually detecting tiny, totally invisible electrical disturbances. Section 1. The illusion of touch, from mechanical to electrical. To really wrap our heads around how we moved away from those clunky mechanical buttons, we have to look at the core technology that makes it all happen. And that is capacitive sensing. Basically, this is a method of detecting touch using changes in electrical charge rather than physical pressure or mechanical switches. Just imagine your phone is projecting a highly sensitive, invisible web of electricity right above the glass. There are no tiny springs, no clicking switches, literally nothing moving mechanically beneath your finger. It's entirely based on constantly monitoring this electric field. But here's the catch. For that electrical field to be disrupted, it needs a very specific catalyst.
Section 2. Your finger as a conductor, the human element. And that missing piece to the technological puzzle? Well, it's you. Here is a simple, undeniable fact. You are an electrical conductor. Because the human body conducts electricity, your finger doesn't just act as a physical pointer like a plastic stylus would. Instead, it actually behaves like a conductive object interacting with the screen's electric field. You are, quite literally, a walking, talking part of the electrical circuit. Now, why is that? It all comes down to basic biology. Our bodies are just full of water, salts, and electrolytes. This specific biological makeup allows our bare fingers to actually hold and transfer electrical charge, which is exactly what disrupts the screen's field. And you know, this perfectly explains why your standard winter gloves completely block this interaction. Regular wool or leather gloves, they're insulators. They don't conduct electricity at all. So to your phone's electric field, a gloved finger simply doesn't exist. You actually have to buy special gloves woven with conductive materials just to bridge that electrical gap. Section 3. The invisible electric field beneath the glass. Okay, so we know you are the conductor, but what exactly are you interacting with? If we were to carefully slice your smartphone right down the middle, we'd see several ultra-thin layers sandwiched together. You've got the protective glass on top, a transparent conductive layer, a sensor grid, the actual display panel, and a backlight or OLED layer at the bottom. But for our explainer today, the absolute most vital layer for touch sensing is that transparent conductive grid. That's where the real magic happens. To make that grid work, engineers use this super fascinating material called indium tin oxide, or ITO for short. Now, the genius of ITO is twofold. First, it's highly electrically conductive, which allows it to carry microscopic electrode patterns arranged in tiny rows and columns. But second, and crucially, it is optically transparent. So it allows the screen to detect your electrical signals while simultaneously letting all those crisp, high-definition images from the display shine through perfectly clearly. It's a real game changer. So, how does this invisible grid actually register your touch? Let's walk through the anatomy of a tap using a system known as mutual capacitance. Step 1. The rows of that ITO grid are constantly transmitting electrical signals, creating a continuous electrostatic field. Step 2. Your conductive finger approaches the glass. Because you inherently have capacitance, your finger literally absorbs a tiny, tiny amount of that electrical charge. This disrupts the local field right at the intersection of a row and a column. And finally, step 3, the columns receive these signals, and a tiny controller chip instantly detects that minuscule drop in capacitance, pinpointing your finger's exact location. Boom, you've launched an app. Section 4, the death of physical buttons, a superior solution. Now, you might be wondering, why did the industry completely abandon physical keyboards and buttons for this invisible capacitive grid? Well, the answer is just a vastly improved user experience. Old tech, think mechanical buttons or those early, mushy, resistive touchscreens that literally forced you to push 2 layers together, They all relied on moving parts. And as we know, moving parts inevitably degrade, wear out, or just get stuck over time. Plus, they usually only supported a single touch at a time. Capacitive screens completely change the game. Because detection is purely electrical, it requires literally zero physical pressure, making it incredibly responsive. No moving parts means durability goes through the roof. But honestly, the biggest win was that it unlocked something older screens just couldn't do.
Multi-touch. This was huge. Because the capacitive sensor grid measures multiple intersections independently, the phone can track 2, 5, or even 10 fingers all at the exact same time. This is the technology that gave us the pinch-to-zoom, fluid photo rotation, complex multi-finger shortcuts, and all those advanced mobile gaming controls we take for granted. It completely transformed human-computer interaction because it finally let us manipulate digital objects naturally, just like we would in the physical world. And the craziest part? It does this incredibly fast, 240 hertz. That is how often some of these premium, specialized controller chips scan the grid for your touch input, 240 times a single second. This little controller chip is essentially the brain of the touchscreen. It's sending pulses, calculating coordinates, and tracking your gestures so rapidly that it practically eliminates input delay entirely. That's why drawing digital ink or scrolling down a web page feels like the pixels are literally attached directly to your finger. But as you can imagine, having a sensor this incredibly sensitive brings up a major engineering challenge: electrical noise. We're talking about a system measuring changes in capacitance so small they're measured in picofarads and femtofarads. It's that sensitive. Because of this, random external electrical noise, like from a cheap knockoff charger, static electricity from your sweater, or even just a drop of conductive water on the screen, can totally distort those electric fields and create fake ghost touches. To combat this, engineers have to pack in intense shielding, advanced filtering circuits, and complex signal processing algorithms just to separate your actual real touch from all that background electrical noise. It's a massive undertaking. Section 5. The future of interfaces beyond the glass. So we've clearly mastered flat glass, but where on earth is this technology heading next? Well, one of the biggest challenges right now is foldable phones. Remember indium tin oxide, that transparent conductive layer we talked about? Well, traditional ITO is actually quite brittle. If you try to fold it in half, it simply snaps. So to make those cool new foldable screens work, engineers can't rely on standard materials anymore. The conductive sensor layer has to bend repeatedly, resist cracking over years of use, and still maintain absolutely perfect electrical performance and transparency. This hurdle is forcing researchers to develop entirely new flexible materials, things like silver nanowires, conductive polymers, and ultra-thin graphene. And the research doesn't stop at just folding screens. The future of capacitive technology is pushing beyond the physical glass entirely. We're already looking at air gesture sensing and hover detection, where the electric fields are actually projected slightly above the screen itself, allowing you to interact without even making direct contact. It's wild. Future devices might use advanced layers to detect your unique skin conductivity, basically recognizing your finger's identity just from a simple tap. They could even track complex 3D gestures in the empty space right above the device. Which leads us to a pretty fascinating question to wrap up our explainer on. As these electrostatic fields become more and more powerful and our filtering algorithms get more advanced, will the touchscreens of the future actually need us to physically touch them at all? The very technology that started out by replacing old mechanical buttons might soon make the physical touch in touchscreen completely obsolete. It's an absolutely incredible evolution of an invisible spark. Thanks so much for joining me for this explainer, and keep wondering about the hidden science right at your fingertips.